Starting from those constatations, we can develop a strategy, and that's what I will explain you now. We have here on the left an apple with an appearance, that I will call the total appearance of the apple. And as I said, I will split my problem in subcategories. I will say, okay, if I want to measure the full appearance of this apple, I need to measure on a parallel way the color, the gloss, the sparkle, all the visual attributes, the translucency. And now, if I look at the color, I can split my problem again with different dimensions of color. For instance, I know that colors is a three-dimensional measurement. I can measure the lightness, the chroma, the hue. For the gloss, I have seen that there is something in the specular. There is a contrast between the diffuse part and the specular part. There is the haze, the distinctness of image, the ability that has the surface to reflect the image of the light source. And all those things, maybe I can split the problem in very simple categories that I will be able to measure with different instruments. That's the strategy. So before you start to measure your object, look at it and try to separate your problem in very small blocks. And then you can try to find, to develop an instrument and a solution for each of them. Once it's done, you have to develop the measurement itself. For instance, if I talk about the chroma here, I can try to measure what is the chroma of a surface, and for this you will need to have artifact objects that will describe that scale. For instance, I will develop different apples, and because I'm interested only in the chroma, I will try to keep the lightness and the hue constant, and I will change the chroma. And I have now my samples that are on a given scale, and I will try to build a visual scale that responds to this collection of samples. So the first thing for this is that I have my different samples. I can do all the measurements that pop in my mind to try to characterize the difference on this scale. For instance, I will use a spectrophotometer, a gloss meter, a Roos meter, a camera, a Gonio spectrophotometer, whatever. Try to find a way, try to find a physical characterization that can allow you to separate those different samples you have developed. For instance, here the reflectance will be a very good candidate because this is mainly blue, this is green, so I will see the peak in the reflectance that will travel from the blue to the green, and I can put one parameter that I will extract from the spectrum, for instance, the wavelength of the maximum of the main peak of the reflectance spectrum. This is one numerical parameter, and I can plot on a physical scale, a physical index, which means the number, and a unique index, according to my 4 samples. And in parallel with this, we will do visual characterization of the collection of samples. We will put those samples in front of an observer, and we will try to collect from this observer its sensation. Because, again, keep in mind that the appearance is in the head of the observer. So how we do this? We do what we call psychophysical experiments. We put an observer in a given light environment that we control. We ask to the observer a very simple question, and that's why I put a part 2 in this lecture when I will explain you, because I guess you're not familiar to this, but it's very interesting. And using psychophysics tools and using statistics, we can also get a number that is on a visual scale. So my observer responds to this scale. My observer can order those samples, for instance. If I give you the 4 apple and I ask you put them in a logical ranking, you will find a way to do it. All answer in the same way. That means that there is something to measure here, and there is something in your head that you can rank. That's ranking we want to access with psychophysical experiments. This is a full field of research. There is a lot of statistics inside, but it can give us a number that is also proportional to the different samples. And once you have this, you have your physical scale on one part and your visual scale on the other part. You can plot the visual scale according to the physical scale. And it's just that those two parts here cancels. And you get what we call a perception model. A perception model put in a relation. Oh, sorry, I need to use my mouse, otherwise all who are online will not see. A perception model put in a relation a physical scale that is measurable with a measurement with an instrument with the visual scale that is here in your brain. And sometimes we just stop here. A lot of industries, in fact, they stop here. They want to measure, I don't know, they want to measure the sparkle. They try to put a physical parameter here that is in relation with the visual perception. They get, of course, different perception models that are all individual because we don't see exactly the same thing. So from the visual experiment, you will not get always the same answer. And even from the physical measurement, you will have an uncertainty on this axis that comes from the quality of the measurement you are able to develop. But in any case, you get here a scale that is different, but hopefully, and it's true, in fact, we all see the same things usually. There is a difference, but those differences are small. So you can be optimistic with this. If it works, you can even go on another step, which is the normalization level. The normalization level is usually done by CIE, and because the ISO delegated all the question on standardization with radiometry and photometry to the CIE. So at CIE level, we can open a technical committee and say, look, all humans, because we have done those experiences in Asia, in America, in Africa, and in Europe, they get something that is very, very similar. It's difficult to make one methodology for each other, but what we can do, for instance, is that we can normalize, we can put a standard observer. It's not you, it's not me, it's a standard observer, and we will develop the methodology for this observer. And of course, you are not the standard observer, but then what you just have to know is how far you are yourself according to this observer. But it simplifies a lot the problem of developing the method at the global level, for instance. But again, you're not forced to do it. If it's just your small business and you want to develop your scale for your small product that you develop alone, you don't have to go to CIE and to go to this step. But if you do it, then you're good because we can develop standard, national standard, international standards that will be just everywhere in the world. And mainly that's the strategy that we have to follow if we want to measure appearance. So I put this slide. I will give you the slides. In fact, I forgot to give it. So I will put the PDF after before tomorrow and send it to you. So the full strategy is the following. You develop, you define your measurement, you split it in easy part, you develop samples that are covering this small part you want to measure. Then in parallel, you do optical measurements. You can even do modeling to summarize the measurements in very pertinent parameters. In parallel, you do visual characterizations and you get visual scales. Then you put those two parts together and you get a perception model. And if you get something that is very stable, you can even go at the normalization level. You get it? Do you have questions so far? If you have questions, just raise your hand and I will stop because it's not supposed to be a full conference of 2 hours long and it can make the things easier. Try to see. So far, no, but I don't see any reason to stick to one dimension. But so far, I don't think there is two-dimensional standard observer. In fact, there is very few standard observer, except on colorimetry. There is no. But and in colorimetry, this is so you have three curves. In fact, you have the RVB, the X, Y, and Z curves that are. But maybe tomorrow, if we do something on gloss, it can happen. There is no objection for this. Yes. Yes. So for color, for instance, in 1931, CIE has developed the color standard observer, and it is defined by three curves, one in the blue, in the red, and in the green. And of course, as I shown you, for instance, it's not enough to describe a full color because the color can be modified by the environment, by a lot of other things. That's what we call the color appearance model at CIE, which are models that are getting more and more complex to take into account those interaction between the measurand, which is the color, and, for instance, the environment. So there is a methodology that is doing, and it goes here, for instance. We do the methodology for one simple thing that allows for the industry to call that their product, for instance. And then we continue the research to be more and more accurate. In fact, it doesn't go necessarily at a normalization level, but it helps the people better in the way they describe the color. And it's always how we do. And it's always progressing. The color appearance model today, there is a so the CIE CAM, how they are called, and I don't know, the fourth one or each time. The last one take into account gloss, for instance.
The physical scale is the physical scale, what the radiometer is going to measure, and for instance, and the visual scale is defined as the color of an instrument, the visual perception of an object, its color, in a given environment. So you define the environment very precisely.
Yes.
So that you can find a visual scale.
Yes. Okay. That's all the work of CIE. For instance, CIE developed, when you talk about daylight spectrums, for instance, developed by CIE, the D50, the D65, and you know those daylight stuff. They are here to standardize the different response, and you can say, okay, I'm looking at that color under a D50 illuminant, and all of us know what it is. You have to put it because color might depend upon this. It's not perfect. It's I don't say that this is the perfect tool. It's just a way to progress, to provide to industry way to further project.
Just a question on the standard observer, because it was defined in 1931. So the world was a bit different back then, but even more. There were a few people that were included, for example, in these the data set. Is there any ongoing work in order to redefine the standard observer or to validate that it's still the case, especially in different parts of the globe?
Yes. In fact, it's even simpler with the V lambda function that defines the photometry. Lambda observer, I will talk about it later, but in fact it has been defined and standardized in 1928. So at that time, the measurement is done by are done with 3 groups, one in England, one in USA, and one in this is the world. So you see, so people starting in the 1960s, they start to say that maybe we should have taken more people, and there has been a researcher who collected measurements almost everywhere in the world, in Africa, in South America, in China. And when they look at it and they compare with the historical curves, they found a very small difference in the blue, but mainly it was the same for everyone because we have the same it doesn't mean that we see exactly the same thing. Because if you are born in the Amazonian forest, a lot of very good way to describe green colors. But it's more semantics than really the capacity of your visual system, in fact. If you get trained, even if you are European, if you get trained, you will be able to have the same accuracy because you have the same visual system. So that's the idea. So, but there was a difference in the blue. And the question was, should we change the V lambda function and we define the full photometry? And the answer has been no at the CIE, because in fact it was not changing a lot of the things, and it would have been a very big change. Why is there a difference? Mainly the answer of the researcher was that at the time in 1928, people were working with QTH lamps or halogen lamps, and the flux in the blue is very low. So it's probably a problem of measurement rather than really a problem of non-representativity of the global. Question is there again, because now you know that to make a white LED, there is the way is to make a blue LED, and then you the UV LEDs that will fluoresce in the green and the red. And so you have a strong signal for some types of LED, a strong signal in the blue that might have an impact, in fact, when it is evaluated by the V lambda, because there is an error in the blue. So it's again on the table at CIE, and we discuss that kind of things, for instance. For the colorimetric observer, because that was your question, the idea today is to move to the LMS colorimetry, if you're aware about this, but it's a colorimetry that is closer to the response of the cones of the retina, and it will solve the problem, I think. So we really have to move to the LMS colorimetry. My answer. I continue? So this strategy has been applied already. Good success stories. The first one is the photometry. That's what we were discussing. The photometry is and the luminous intensity, the candela, is a measurement that try to reflect the intensity of the light seen by a human observer. And that was the measurement. So how we did solve this? We did a psychophysical experiment at different levels. So we tried to see for each wavelength, what is the sensation of light that it gives in your brain. And for instance, I can do the experiment with you. It's very simple. I put one given wavelength. This is in the blue, so it's not just one single wavelength, but anyway. And on the right part, I will ask you to give me the sensation of color, natural color, that gives you the blue. For instance, here maybe you have the idea that the blue is lighter than the gray, but if I increase the lightness of the gray, you might have at the moment the sensation that you have a kind of equivalence between the two halves. When is it? E, C, E. Not E, come on. Between C and B, B half. Now I go on another part of the spectrum. Stop me because I don't have more. Can influence a bit. Something around here. And now I go on the red. Oops, sorry. So you're not very active. When I do it in a full amphitheater at CNAM, I have people who are shouting, yeah, B, C, D. And so maybe C, maybe D. Let's go on D. Yes, almost. So you see, I can get from my observer, in fact, very easily an answer. It's not easy here with the projector and everything, and it's not even the best way to do it, because when we by flickering, in fact, it works better. But it's possible to get a consensual answer from people, and so now I have an idea of how for each wavelength, what is the sensation of brightness that you get according to a reference, which is the spectrum of my gray. So you have compared those wavelengths according to always the same spectrum. And so if I put this on a graph, according to the wavelength, I can plot the sensation of brightness that you get. And I have 3 points. Well, 3 points, okay, it's not a lot, but I can, if we have time, we can do 50 points, and we will get something smoother. In fact, we will get something which is something like this. And it's almost the same for all of us, so we can decide to normalize and say we all see the same thing, and this is the history of V lambda. This is the history of photometry. Then we just put a value, because it was relative to gray, we can put a value on the gray, and then we get an absolute unit. And the absolute value today is 638 lumens per watt, for instance, in the international system. And it worked so well that we have in the 7 units of the international system of units, we have the candela, which is in fact the quantity that represents the human in this system, the sensation, all the field of measurements that are linked to the sensation. So this is a good story. Now, when we have the quantity, which is the luminous intensity in the definition, we can develop derived units as for the meter or for the electricity department. So we can define the flux, the radiance, the irradiance, whatever. We can develop instruments that are doing this. We can develop national references for all those quantities, and we have a full meteorological system based on a visual scale, in fact. We can do the same with color, and it has been done also, but now you need 3, because there is 3 axes on the color, the brightness, the lightness, the chroma, and the hue. You can have 3 curves. Again, normalization by CIE, and you have your full system of colorimetry that is coming with portable spectrophotometer, with calibration tiles to calibrate your photometer, and with national spectrophotometer at National Metro. Same for gloss. You can take the gloss, you can take a gloss meter, you measure the visual sensation, you try to put normalization. So you don't have for gloss a standard observer because it has not been done, but at least there is a way to make the measurements, and there is the development of gloss meters, there is standards, and that's where we are today. There is primary gloss meters. So that's the full way. Start with your measurement, you develop your samples, you make in parallel visual characterization, optical characterization. You find a way to get perception models that are strong and stable. If they are very strong, you can even go to a normalization level. And once you are here, for industrial, it is perfect to develop a full collection of instruments, portable or lab instruments, whatever, like spectrophotometer. Then those instruments, to be stable, they are calibrated against standard artifacts that are kept at the national metrological level. And now you can start again because you measure better the color, and you can start to look at the interaction between color and gloss, for instance, because you have made, you are on a new step, and you can start again the process to try to be more and more accurate. This is the strategy for the measurement of appearance, and that's the end of the first part of the lecture. You have questions?